So the audio on the previous video was really low, so I decided to make a second version of it. We're dealing here with a Poncelet pair with an external black ellipse and an inner circle that is concentric with the external. And we're looking at the three periodic family interscribed within this pair, the Poncelet family, P1, P2, P3, these blue triangles. A first emerging property from this one-dimensional triangle family is the fact that its circumradius, I'm drawing here the circumcircle, this dashed blue circle, its circumradius shown up here is invariant over the family, big R. By definition, small r is invariant, right? The incircle is stationary, the brown circle. Another emerging property here related to the incircle is that the circumcircle is that the circumcenter x3 moves along another concentric circle, this dashed black circle here. If I vary the aspect ratio of the family, so now making a very elongated, highly eccentric black outer ellipse, my circumradius continues to be invariant at 3.06 up here, and the circumcenter continues to move along a circle. There is a particular aspect ratio, looks like it's close to 2.4, such that the path of the circumcenter is equal to the caustic incircle. Okay, now we want to talk about excentral circumhyperbolas or circumellipses. What is an excentral circumellipse? Let's draw the three excenters. The three excenters are the vertices of the so-called excentral triangle, whose sides are perpendicular to the bisectors at each vertex. So if you imagine a bisector, each one of the vertices P1, P2, P3 of a generic triangle, the excentral triangle shown here as dashed green has sides which are perpendicular to each one of the bisectors. So I can watch that family. The three green dots, the vertices of the excentral triangle, are known as the excenters. Okay, now let's take this family back to a rounder shape. Let's zoom in a bit. Now what I want to do is I want to calculate, for example, I'm going to take two vertices. I'm going to take the three vertices, P1, P2, P3, and I want to run an ellipse through these three vertices. So these are three constraints. And I want to specify the center of that ellipse to be one of the excenters. For example, this one. So let's draw it. Actually, I chose this one here on the right. So here's an ellipse shown orange here, centered on one excenter, which passes through the three vertices of the family. So I can watch that circumellipse, defined as we just did. And I can also notice, oh, I forgot to mention, since both the circumradius, big R, and the inradius are constant, this ratio is constant, this implies that the sum of cosines of this family is constant. So you can see that there. Now going back to the circumellipse, let's go ahead and take the circumcircle out. The area of the circumellipse and its general shape are not invariant, so it's changing the length of both semi-axes and it's also changing the area. However, if I repeat this construction, the circumellipse construction, meaning I want an ellipse that passes through the three periodic vertices and is centered on this excenter and another one which is centered on this one, I get this triad, right? So I get a triad of ellipses, like so. And the area of these three ellipses, each one of them has a distinct area. You can see here A sub I, there's three distinct areas. And they're all varying. However, the sum of those areas is constant. It's invariant over the family. You can see here that this is the sum. And I can also report the ratio of the sum of areas by the area of that black ellipse. So I'm reporting that being reporting it here as 9.7 something. A0 is the area of the central ellipse. Okay. Now I just want to show a couple of special cases. When the central ellipse becomes a circle, i.e. A over B equals 1, so I have the so-called concentric Poncelet pair. You get this threefold symmetry, right? My three periodics are equilaterals. The excentral triangle is an equilateral as well, the dashed green one. The three ellipses become identical, just rotated versions of each other. And it turns out that the sum of their areas reported here is still constant and is equal to 9 times the area of the black circle, meaning that each one of these ellipses has 3 times the area of the black circle. Another nice example is when we make the aspect ratio of this ellipse, of the outer ellipse, be 2. And this happens at, let's find that point, or that aspect ratio. So there it is. We've manually found an auxiliary. There's an auxiliary constant here that sets this aspect ratio of 2.0. So now my black ellipse has aspect ratio 2. Let's animate that. The sum of the three areas is still invariant. However, at this special aspect ratio, the ratio of the sum of areas by the area of the black ellipse is, interestingly, exactly equal to 10. Okay, so we got 9 for the concentric circles and 10 here. Okay guys, I hope you've enjoyed this video. I hope the volume level is better than in the previous one. And see you on the next one. Thank you.